Okay. So the presentation is number 12, is SARIMA forecasting. We're gonna be talking about forecasting for the SARIMA models, but we will talk about all the theory behind in the context of ARIMA models. Because with SARIMA, with seasonal time series, the same things happen, but the notation becomes a lot more complicated, okay, in the notation, because we have the two autoregressive polynomials, the non-seasonal, the seasonal polynomial, the two moving average polynomials, which is the non-seasonal and the seasonal moving average polynomials, plus the two types of differences, the normal differences, let's say, in the seasonal differences. So we'll focus on the ARIMA models without the seasonal component to develop the theory. Okay. Now let me get my iPad, because we have to draw stuff here. Okay. Now we're going to call WT, and let's suppose that WT is already a stationary time series. Okay, so WT may be the result of the difference, okay, difference of order D, of a transformed time series. So maybe we have to stabilize the variance first, and we have to make a transformation, probably a log transformation or whatever. And then we have to take differences so that to make sure that that transformed series is already stationary. Okay, so the series, if it's a stationary time series, then we know, we've seen that when we talk the stationary time series, that we can represent the series as a linear combination of some weights that we call psi 0, which is 1, psi 1, psi 2, psi 3, multiplying at minus 1, at minus 2, at minus 3. So it's a linear combination of random shocks, essentially. That meets that representation because of stationarity. Now, let's suppose that we start at origin T. Okay, so we have a series, and we want we're standing now at time T, and we wish to forecast H periods ahead. So we will call that what we want to forecast is observation WT plus H. Okay, that's what we want to forecast. We will denote by W tilde T and in parentheses H, W tilde at time T of H, H being the lead time, any forecast which results in from a linear combination of the previous values of WT. Okay, so any forecast that is computed as the linear combination of previous values of WT will denote by WT tilde. Okay. Since it's a linear combination of the values of the WT values, then it is, of course, a linear combination of the ATs, because remember that each WT is just a linear combination of ATs, AT minus 1, AT minus 2, AT minus 3, and so on. So it's a linear combination of the ATs. That's an important thing. So that's any forecast which results as a linear combination. What we want to do is not work with any forecast, but we want to work with an optimal forecast, okay? A forecast that will minimize the mean square error. That's the one that we want to develop. So we'll denote by WT but hat, with the hat instead of the tilde, of H, the forecast H periods ahead, or WT, that we estimate that minimizes the mean square error. That's going to be the optimal forecast, the one that minimizes the mean square error. Remember, we're working with continuous, if the WT is a continuous type variable. So if we're going to forecast that, the criteria would be to minimize the square error, the mean square error. Now, if that is the forecast, W hat minimizes the conditional expectation E sub t. That's why we use the notation to indicate that we are computing the conditional expectation at time t of Wt plus h, which is the actual observation that we will have at time t plus h, minus its estimate, its optimal estimate squared, that squared. That's what we want to minimize, the conditional expectation of the actual data, the actual what we will observe in the future, h periods ahead, and what we will estimate to be the observation h periods ahead. Okay, and the W hat tilde will be the minimum then of all the estimates W tilde, which are linear combinations of the ATs. So we'll take all possible estimates that result from a linear combination of WTs, and that will be calling the optimal forecast, and that will be the one that minimizes the squared errors in expectation, conditional expectation. By saying conditional expectation at time t, what we mean is that's the expectation given that we know WT, WT minus 1, W2 minus 2, and so on. So given that we have information up to time t, that's the conditional expectation of the error in forecasting. And the W hat t of h will be the minimum, will be the linear combination of the ATs or the WTs in the past that minimize the square error, the expected condition, the conditional expectation of the error, okay, of the square error. That's how we're going to find define the optimal forecast. Now, what we're saying is that the expected value conditional on t of Wt plus h minus Wt tilde of h squared will be the expected value of Wt plus h minus W tilde of h minus the estimate, the expected value of the observed, the actual value minus its estimate, given that we know observations ZT, ZT minus 1, ZT minus 2, and so on. That's what we refer to as conditional expectation. Now, WT tilde and WTH, WT hat, both have to be of the same form. Both are linear combinations of the ATs. They are linear combinations of the WTs, and therefore they are linear combinations of the ATs, which is the white noise, right? AT minus 1, AT minus 2. So that's a general form for a forecast. That's a linear combination of prior observations, okay? Now, the problem to find the optimal forecast then is to find the values of these coefficients, C, H, CH plus 1, and so on. We want to find these values that satisfy that the conditional expectation is minimal among all possible linear forecasts that result as a linear combination of the previous WTs and previous ATs, against the previous ATs. Okay, we're doing fine up to this point.
And teacher, I think last class we saw that the coefficients could be like a geometric series, like so they give more weight to the recent observations and less to the last observations. This is similar or it's different?
Well, it's going to be essentially similar. The weights are going to be given by the estimates of the coefficients of the model. Okay. But there's the other one is just, let's say, is sort of an empirical solution, right? it makes sense that the last observations weight more than the observations that are really far behind in time. So that's empirically, that's the right approach, and that's how that forecasting method based on the exponential smoothing comes about, because empirically it makes sense. Now here this is more formal, and this is more formal in the sense that we're working now under the assumption the ATs are normally distributed, they're independent, and what we want to do is find the forecast that minimizes the expected value conditional on what we know up to time t of the error that we make when we forecast. Okay, so the conditions on the coefficients are really based on minimizing the mean square error.
All right, thank you.
Okay, most of the models will do that. They will, if you look at the coefficients of a pure autoregressive model, in general, you'll see that phi1 is larger than phi2 in an AR2 model. Okay, but that's not necessarily the case, because it depends on what minimizes what maximizes the likelihood. That's what we obtain the estimates, and in the case of the forecast, what minimizes the mean square error. Okay, so as a result of trying to minimize this, we will obtain the model that minimizes this mean square error for forecast. And that will be the forecast that we'll be using to estimate what the values of the series are going to be in the future. I don't know if that helped clarify your question or not.
Yes, thank you.
Okay. Now, to obtain the solution, remember that we assumed that WT is stationary. If it's stationary, I can express WT as a linear combination of the psi 0, psi 1, psi 2, multiplying AT minus 1, AT minus 2, AT minus 3, and so on. So WT plus H, I can express it as the sum of psi sub j, AT plus J plus H minus J, from J equals 0 to infinity. Okay, that's because the process is stationary, and I can split this sum into components. See, I can split this sum into components. The first component is using, let's see, for example, it goes from J equal to 0. So it will be psi j, for example, if j is equal to 0, it will be AT plus H, right? If j is equal to 1, it will be AT plus H minus 1. If j is equal to H minus 1, it will be AT plus H minus H plus 1 will be AT plus H minus H plus 1, that will be AT plus 1, right? So this is what AT plus H we don't know, because that's in the future. We know we are standing at time t, so we don't know what that is. So this is the future, and here, for example, here, J is equal to H. When J is equal to H, this is AT plus H minus H, that's AT, and then it will be AT plus H minus 1 minus, when J is equal to 1, AT plus H minus 1, AT plus H minus 2, and so on. Assuming here that psi 0 is equal to minus 1. So I'm essentially expressing the sum, the WT plus H, as the sum of two terms. The terms that are in the past and the terms that are in the future. Okay? That's the information that we do not know at time t, and this is the information that we know at time t. So we're doing that's what we're doing. We're splitting the sum into two terms. The part that we don't know because we're standing at time t, so we don't know what happens at time t plus 1, t plus 2, and so on. And another component that has the information that we know up to time t. Okay. Now, why we do this same? Because we want to be able to express now the expression that we want to minimize is we want to minimize the wt plus h, which is what we will observe at time t plus h, minus its estimate, which is a linear combination of the ATs. And I split that as these two terms, okay? I split that as these two terms. In this case, this is what we do not know. So that'll be the sum from j equal to 0 to h minus 1 of psi j squared, at squared, at plus h minus j squared. But and this part here involves the ATs that we already know, the ATs that are in the past, okay? When j is equal to h to infinity is what we have in the past. And in that case, that will be, in this case, we do not have CJs, right? We do not have CJs because the linear combination WT tilde of h can only involve the terms up to time t, cannot involve times but beyond time t, okay? And so we want, this is what we want to minimize. Now, of course, there's no way, the psi j's are referred to what we don't know, so we cannot choose the psi's to minimize that. What we have to do is choose the CJs that will minimize this whole thing. So in essence, what we want to minimize is this part here, okay? We want to minimize the sum from j equals to from h to infinity of psi j minus c sub j, which is the coefficient that we don't know. And we'll determine that by minimizing that sum of squares. Okay. Are we okay up to this point?
Yes,
I
sure.
guess silence says we're okay, right?
Yes.
Now, recall that the expected value of AT and AT plus J, AT plus I times AT plus J, that's going to be equal to 0 if I different from J, okay? So the only cases where that expected value is different from 0 is when the subindex of A coincides, and then we have the variance, sigma squared sub A. So remembering this, and we can obtain that the conditional expected value of the difference between the actual observation and its forecast squared is this sum of psi j sigma squared A plus the sum psi sub j plus c sub j squared is sigma sub A squared, and that will be minimal when what happens? That will be minimal when Cj, each of these constants, is equal to the corresponding psi sub j. Okay. Of course, we don't know what psi sub j is. Okay, but the c sub j that will minimize that will be the c sub j that makes this term equal to 0, because we cannot do anything to minimize this thing. We can only work with the right side of the equation to minimize that the conditional expectation. But to minimize that conditional expectation, we need to have that Cj, the coefficients are minus psi sub j, which are the weights of that linear combination of the ATs that represent the WT. So we need to make sure that that's equal to, Cj is equal to minus psi j, for j equals to h plus 1, and so on. So for all for any value of h that we want to forecast, for any lead time we want to forecast, the coefficients of that linear combination that will minimize the mean square error will be the coefficient that's equal to minus the corresponding psi weight. So the conditional expectation of give a time t of wt plus h minus w hat, this is w hat, this is w tilde, that's any estimate. But when we have w hat here, that would be the one when Cj minimizes psi sub j, and that would be only this term here. See, this term is this term here. Because if we achieve the minimization of this whole thing, we'll be able to have Cj equal to minus Cj, so that this part will disappear. And the conditional expectation of the square error in forecasting h periods ahead will be given by just the sum of the psi sub j squared from j equal to 0 to h minus 1 times the variance and sigma square sub a. Okay. So remember, we are with this expression comes from here. From this one here, okay? From splitting the sum in the two terms and then taking the expectation, the conditional expectation. Okay. So that would be that would be the optimal forecast. And the conditional expectation of Wt plus H minus W hat squared will be this thing here. And that'll be the minimal of all linear combinations of the ATs, of the previous ATs, that minimize the square error conditional on T. It's always conditional on the fact that we know the information from time T, T minus 1, T minus 2, T minus 3, and so on. Okay? Now, by the definition of conditional expectation, and given the properties that we know that of A sub T, the expected value of AT plus H minus J will be AT minus H minus J if J is greater than or equal to H. That is, if we are in the past, then the expected value of AT plus H minus J is the error that we already had in the past, is the AT that we had in the past. Okay? So if J is equal to H, then the expected value of AT is AT, because we're at time T, so we know what AT is. If the expected value of AT, if J is equal to H plus 1, then we'll have T plus H minus H plus 1 will be AT minus 1. Okay, so that'll be expected, that'll be AT minus 1 because we know AT minus 1, because we know all the information up to time T. And therefore the expected value, the conditional expectation is AT minus 1. Whereas if J is greater than, if J is less than H, then we're in the future and we have assumed that the ATs are random shocks, are white noise, so therefore they have mean 0. So the conditional expectation of AT plus H minus J when J is less than H, that is, we're in the future, that expected value is 0. Okay? So we know that. Then the expected value conditional on T of the Wt plus H, which is what we will observe at time T, its expected value conditional on T, we express it as the expected value of the two sums that we already saw. Expected value conditional of T from J equal to 0 to H minus 1 of psi J AT minus plus H minus J minus this expected value of AT psi sub J AT plus H minus 1. And remember that this is what we do not know. This is the future, and this represents the past. The past and today, let's say. So this expected value is going to be since the process stationary, the sum of psi j's will converge and all that, so that will be the sum of these expected values, and that term disappears because its expected values are 0. Okay. Now, it is clear then that the optimal forecast, WT hat, H periods ahead, is the conditional expectation of WT plus H, given that we are at time t, given that we know all the past up to time t. Okay, and that's a very important result. The optimal forecast is the conditional expectation of WT plus H, given that we know all the information from t, t-1, t-2, and so on. Since WT plus H, we already saw that we can express that thing as the sum, and it's the sum of these two terms, with psi null equal to -1, then the forecast error with origin t, H periods ahead, will be the difference between WT plus H minus the optimal forecast, W hat sub t, H periods ahead. And that difference between WT plus H and WT hat is just going to be the sum of the psi j's, AT plus H minus J, from J equals to 0 to H minus 1. It's just this term here. That's the forecast error at origin t for one H1 period ahead, 2 periods ahead, and so on. Whatever value of H we have. Okay. Because this optimal forecast is essentially the conditional expectation of t of WT plus H, given that we are at time t, that we know all the data up to time t. Okay, are we okay so far? Okay. If there's any doubts or anything, it's better to stop now and go back than end up with confusion on the concepts here. Okay, the principle is very simple. We're trying to forecast, and we choose among all forecasts that are linear combinations of the past. We want to choose the forecast that minimizes the mean square error for that forecast. Okay, that's the optimal forecast, and that turns out to be the conditional expectation of WT H periods ahead, which we don't know, but that would be the conditional expectation, that given that we have information up to time t. Therefore, the expected value, conditional of t, on this forecast error, H periods ahead, is going to be 0, okay? Because this is going to be the expected value conditional of t of WT plus H. This is W hat, right? What we're saying there is the expected value conditional of t of E sub t H periods ahead is the expected value conditional of t of WT plus H minus WT hat. Well, WT hat is exactly this one. Okay, so that's equal to 0. Okay. And the variance of the E of H is just going to be the sum of the psi j squares per times sigma squared, times sigma sub A squared. Okay, which represents the psi j's, remember, are the weights for that representation of a stationary process in the future. It's what we don't know. Okay. So therefore, the variance of the forecast error h periods ahead minus the variance conditional on t of the forecast error h minus 1 periods ahead will be just the difference between the variance of ET h periods ahead is going to be this thing here, right? So this is going to be the sum j equals 0 to h minus 1 of psi j squared sigma squared. And that's this term. In this term, to h minus 1 will be the sum of from j equal to 0 to h minus 2 of psi j squared sigma squared. So that's equal, that's psi j h minus 1 squared times sigma squared, because all the other terms just cancel themselves for h greater than or equal to 1. There, what can we say about from this expression? See, this the variance, the conditional variance at time t of the forecast error h periods ahead is essentially one constant that we don't know, but that's a constant. Psi is a constant times the variance of a for h greater than or equal to 1. Okay, and if h is equal to 1, what happens then? If h is equal to 1, then the forecast error 1 period ahead is going to be wt plus 1 minus w hat t 1 period ahead, and that will be at minus 1. So the forecast 1 period ahead are white noise. The forecast 1 period ahead are white noise. So therefore, the forecast errors 1 period ahead are uncorrelated, since white noise is uncorrelated. Okay. So this error, forecast error, when we're forecasting 1 period ahead, is simply at minus 1, at plus 1, and that's equal. Since the ATs are white noise, they are uncorrelated. So the forecast errors 1 period ahead are uncorrelated. They are not correlated. But in general, the forecast errors for h greater than 1, 2 periods ahead, 3 periods ahead, and so on, they're going to be correlated. Why? Because remember, the forecast h period ahead is wt plus h minus wt hat of h, and it's the sum. Okay, so this is like an MA model with h minus 1 terms, right? This is an MA1 model with h minus 1 terms. So the ET of the forecast h periods ahead for h greater than or equal to 2 are going to be correlated. Okay. Remember that when we have an MA2, remember that for an MA2, remember what the autocorrelations at lag 1 and 2, they were different from 0, right? So they're correlated. For an MA3, the autocorrelation function for an MA3 have the first 3 autocorrelations being different from 0. So they are correlated. Okay. So for a fixed h, then the forecast errors follow an MA-H1-1 process. Okay. So we can always expect to see some sort of correlation in the errors when we do forecasts several periods ahead. We can always expect to see because there is some correlation among the errors for h periods ahead when h greater than or equal to 2. Now, if the origin remains fixed, the forecast errors for several periods ahead. So previously we said if we fix h. Now, we don't fix h, but we do the forecast errors for 2 periods ahead, 3 periods ahead, 4 periods ahead, and so on. They are also correlated. Okay. So when we do a forecast for several periods ahead, there will be some correlation. Okay. For fixed h, when h greater than or equal to 2, is definitely that there is some autocorrelation in the forecast errors. But when we generalize and we do it for h equal to 2, 3, well, therefore, in that case, actually starting from h equal to 1, if we do forecast errors 1 period ahead, 2 periods ahead, 3 periods ahead, all those forecast errors are going to be correlated. Now, let's go back to our model. Okay, we never know the psi weights. Okay, so we don't know the coefficients that minimize the conditional expectation. So let's consider the model. We said that WT is stationary, so we can express the model as phi of B WT minus theta of B AT, where phi of B is the autoregressive polynomial and theta of B is the moving average polynomial. Okay, it's stationary, so therefore the roots of phi of B will lie outside the unit circle. Then the estimate, the optimal estimate, the optimal forecast, h periods ahead, we know that that's a conditional expectation of WT plus h, of what we will observe h periods ahead. So that conditional expectation, if we express now this model in its polynomial form, well, that'll be the conditional expectation of phi 1 WT plus h minus 1. Remember, it's phi 1 zt minus 1 plus phi 2 zt minus phi 2 in the other side of the equation, minus phi 2 zt minus 2, and so on. We put everything on the right side, and we had phi 1 WT plus h minus 1 plus up to phi p WT plus h minus p plus AT plus h. That's and then there comes the moving average terms, minus of theta 1 AT plus h minus 1 minus theta 2 AT plus h minus 2, and so on up to theta q AT plus h minus q, because we have assuming, of course, that the order of the autoregressive polynomial is p and the order of the moving average polynomial is q. Okay. So if we now compute this expectation, that will be phi 1 times the expected value of WT plus h minus 1 plus all the way up to phi p times the conditional expectation of WT plus h minus p plus the conditional expectation of AT plus h. Okay. Minus theta 1, the conditional expectation of AT plus h minus 1 minus all the way up to theta q, the conditional expectation of AT plus h minus q, given that we are sitting at time t. Okay, we know from time t and to the past. So now, what are these conditional expectations? The WT plus h minus j in general, because we have t plus h minus 1, t plus h minus 2, t plus h minus p. Well, the conditional expectation of t plus h minus j, if j is greater than or equal to h, okay, then we will have the conditional expectation will be the observation, right? Because here we're in the past. So if h is equal to 1, I have t plus h minus 1. If h is equal to 1, sorry. If h is equal to 1, and for j is equal to 1, I have t plus 1 minus 1, that'll be WT, and then minus 2, WT minus 2, WT minus 3, and so on. So that's already in the past. So it's what we observed. And this second term here represents the future. And we know that the conditional expectation of WT in the future is the optimal forecast. Okay, it's W hat of time T of H minus J. Okay, how many periods ahead we are forecasting. So if J is less than H, that will be the result of this conditional expectation. And for the ATs, again, what happens is for the past, it'll be the values in the past. And the values of the ATs in the past are the errors for that model gave us to estimate a past observation. We know what the past observation was, so we know the WT plus H, and we subtract what would have been its optimal forecast, and that will be the error. This is the same thing as the error H periods ahead, right? If J is greater than or equal to H, we're in the past. So the error is the difference between what we observed and what we estimated. And if we're in the future, the expected value of this AT plus H minus J are 0, okay, because they're white noise. Okay. Let's look at an example, one model in particular. Let's look at this model, which is an ARMA 1-1. With these coefficients, phi1 is 0.6 and phi2 is minus 0.2. Theta 1 is minus 0.2. Okay. Then we can express this model as WT equal to 0.6 WT minus 1 plus AT plus 0.2 AT minus 1. Okay. Now, what will be the forecast? The forecast one period ahead is going to be the conditional expectation of WT plus 1. And that conditional expectation of WT plus 1 will be 0.6. The conditional expectation of WT, remember, WT plus 1, all I'm using here, this is just algebra, okay? The WT plus 1 is equal to 0.6 WT minus 2 plus AT plus 1, then plus 0.2 AT. AT plus 1 minus 1, that'll be AT. Okay, so that's 0.6, the expected conditional expectation of WT. I'm sorry, I'm T plus 1. If this is still, I wrote it wrong here. Sorry about that. I'm erasing this whole thing. So WT plus 1 will be 0.6 times WT plus 1 minus 1, which is WT. Then plus AT plus 1, and then plus 0.2, AT plus 1, AT plus 1 minus 1 is AT. Okay, that's what we have here. And that's 0.6 WT, because we know we are standing at time T. So we know what WT is. We know what the current observation is. Plus the conditional expectation of AT plus 1, and that's equal to what? That's equal to 0, right? And the other term is 0.2 conditional expectation of AT at time T, and that will be, again, we're sitting at time T, so the expected value of AT is the actual error at time T, which is what we observe now, the current observation, minus its forecast that I did, the forecast that we computed one period before the forecast for today, because that's 0.2 times this error, the forecast error. That will be with WT one period ahead, the estimate, the optimal estimate of the optimal forecast one period ahead. If we go 2 periods ahead, we do the same thing. We replace what WT plus 2 is, and that we will get, that's 0.6 times the conditional expectation at time t, or WT plus 1, plus conditional expectation at t plus 2, plus 0.2 to conditional expectation of AT plus 1. And now, this is conditional expectation is the optimal forecast 1 period ahead. Okay, because we already saw that the optimal forecast is the conditional expectation. And then this will be 0 because AT plus 2 is in the future, and its expected value 0, and this 0.2 times 0, that also will be 0. Okay. And in general, if we look at H periods ahead, the forecast, the optimal forecast H periods ahead will be 0.6, the optimal forecast H minus 1 periods ahead for H greater than or equal to 2. Okay, so this generalizes for H greater than or equal to 2. Okay, is that clear?
Teacher, could you repeat why the expected value of AT was that difference?
Okay, because remember, we're standing at time t. So at time t, we know what WT is. We know what WT is. And the estimate of AT is going to be the difference between the actual value that we observed today minus what we forecasted yesterday that would happen today.
Okay, all right.
Okay. This is the optimal forecast when you're standing at time t minus 1. So t is today. It's the optimal forecast that you computed yesterday, one period ahead. That'll be for today. Okay, that's a forecast error for 1 period ahead.
Okay, thank you.
Yeah.
Yes.
Okay. Now, in general, we'll observe that WT1, 1 period ahead, involves the forecast, the optimal forecast at time t minus 1 period ahead. And this in turn will involve W hat t minus 2 1 period ahead, because this already is giving you a sense of recursiveness. Here you can see that this is a sense of recursiveness. This WT 1 period ahead depends on WT plus 1 on this conditional expectation at time the WT plus 1. Then this WT at 2 periods ahead involves the optimal forecast 1 period ahead, and WT plus WT of H periods ahead, WT hat H periods ahead is the conditional expectation. It involves 0.6 times H minus 1. Let me connect my lab because I'm losing power. So WT 1 period ahead involves WT hat minus 1 at t minus 1 period ahead, and that involves itself W hat t minus 2 1 period ahead, and so on. WT minus 1 period ahead is 0.6 WT minus 1 plus this thing here, right? We already saw this thing. And we continue this way, and if we continue developing this thing and substituting what each of these WT hat t minus 2 1 period ahead, replace that what it is by what we saw last slide, then do that for WT minus 3, WT minus 4, and so on, up to W1, up to the forecast that you make at period 1, at the first period, 1 period ahead. Now, here the issue is that we do not, our series starts at W1, right? Our observations start in W1, W2, and so on, up to WT. So we don't know this W0, what will be the forecast that we make at time 0, 1 period ahead. We don't know that, okay? So let me see, I'm against my window here. I'm turning this thing a little bit here. So we will always assume that to be able to obtain this thing, we will assume that the forecast of W1 that we supposedly make at time 0 will be the first observation that we have. Okay, so the forecast error at time 1 period ahead will always, at time 0 1 period ahead, will always be the first observation. Okay, therefore we can obtain the forecast, the optimal forecast, h periods ahead for h greater than or equal to 2 in a recursive way. So we have W hat 1 period ahead is 0.6 W1. Then W hat 2, 1 period ahead is going to be 0.6 W2, which is the second observation, minus 0.2, our optimal forecast, one period ahead time, computed at time 1, at t is equal to 1, all the way up to WT, which is what we're standing now at time t, is 0.6 WT minus 0.2 WT minus 1 period ahead. Okay? Now, all we did now is for stationary time series, right? And in fact, that's what we're going to be doing. We're going to forecasting stationary time series. And we will always assume that we can, if the series is not stationary, we can make it stationary through either a transformation or taking the proper number of differences, or both. We may have to do a transformation to make the variance constant. For example, a Box-Cox, the family of transformations, use that, and then take the differences that we need to take for so that the series is stationary. So that's the type of non-stationarity we'll be dealing with. The one that we can eliminate by doing a transformation and taking differences. Now, let's suppose that we have a homogeneous non-stationarity, and we cancel that with d is equal to 1. Okay, so let's suppose that we have to take one difference. Then the forecast, h periods ahead, can be obtained as we just discussed it, because that once we take the difference, the series is stationary. Okay? And the optimal forecast for the series t of zt are going to be the conditional expectations at time t of wt plus h, and that's again conditional expectation of t, the transformed version of ct plus h minus the transformed version of ct plus h minus 1. Okay, because remember that wt plus h is ct minus ct minus 1. Wt is zt, we're saying we're taking one difference, so wt is zt minus zt minus 1, right? So the conditional expectation wt plus h is going to be this difference. So that the estimate, the optimal forecast of the transformed zt h periods ahead will be the conditional estimate of the transformed zt plus h, the conditional expectation at time t of the t of zt plus h. And that will be, it's the same reasoning that we used earlier. That will be, if h is equal to 1, that will be the transformed series ct minus its optimal forecast, 1 period ahead, if h is equal to 1, and if h greater than or equal to 2, then it will be the optimal forecast, h minus 1 periods ahead, plus the optimal forecast, h periods ahead, if h greater than or equal to 2. It's the same logic and same reasoning that we used earlier to compute this optimal forecast of the transformed series z sub t. Okay. So a more direct way to obtain this forecast comes from the fact that the optimal forecast of the transformed ZT plus H is its conditional expectation at time t. Okay, that in general is going to be the case. The optimal forecast is going to be the conditional expectation at time t. Now, if we have the model of this form, okay, I changed the phi for this other phi, okay, because we're working now with t of zt, okay, the transformed version of zt. That's phi of b t of zt is equal to theta of bat, and phi of b is now the dth difference of phi of b. So for general, if I take d differences, then this model I'm going to denote by phi of b at the difference operator times the autoregressive polynomial phi. Okay, so I put all those together, and then if we do that, then we can verify that t of zt, the transformed zt, h periods ahead, the optimal forecast of that transformed series is going to be the conditional expectation of t of zt plus h. That's always true. The optimal forecast is the conditional expectation. And that will be, if I replace these values of the coefficients of this polynomial, that will be phi 1 times the conditional expectation of the transformed series in period t plus h minus 1 plus phi p plus d. Why p plus d? Because we have the autoregressive polynomials of order p, and I'm taking d differences. So when I multiply these two polynomials, I get a polynomial of order p plus d, right? This gives me a polynomial of order p plus d, because I'm taking d differences of a p order, of an order p autoregressive polynomial. So that times the conditional expectation of t zt plus h minus p minus d. Okay. Remember, when we take one difference, we lose one observation. We take two differences, we lose two observations. So if we have, if p is equal to 1, then we need the prior observation, so we can start at 2 only. But if p is equal to 1 and v is equal to 1, then my forecast can start at time equals 3, right? Because I need the first two observations to do the forecast. So that's phi plus d, conditional expectation of this transformed form of zt h minus plus h minus p minus d, plus the conditional expectation of at plus h. Okay, that's going to be the forecast, the optimal forecast, h periods ahead for the transformed series. And the expected value of t, conditional on t, of the transformed ct plus h minus j, this expected value is going to be, again, if we're in the past, here we are in the past, this is we're today and the past, is what we have already observed as the transformed value of the series. And we're in the future, that's the future, this conditional expectation is going to be the t of zt h minus j periods ahead if j is less than h, okay, in the future. So the conditional expectation, because the conditional expectation is the optimal forecast. And the expected value of this term, at plus h minus j, will be, if j is greater than or equal to h, it's the past, it's today and the past. So that will be the errors that I made forecasting what we already know. Okay, those are the errors. Those are the conditional expectations of at plus h minus j for j greater than or equal to h as long as we are in the past. But if we are in the future, this expected value is 0 because AT is white noise. Okay. Okay. I think I'll stop here because that's a lot. It's a lot of concepts, and I need you to digest these concepts, these ideas. I would like to ask you to review these few slides that we've covered so far. Just review them. If you can turn on your cameras, that would be great, so I can see you at least for a few minutes. And when we meet here in the campus, we'll recognize each other. Although with these masks, it's very difficult to recognize people just unless you know their eyes very well, right? So, are there any questions so far up to this point?
I don't think so, teacher.
No, everything's clear.
Right now, it's okay.
So far,
Pardon me, Edson?
so far everything clear.
Okay, good. Good. It's important that you have all these concepts clear to understand how we compute this optimum forecast and why they are optimal and so on. Okay? So I'll see you tomorrow.